Hi, hi students. So in the last class, we are discussing, already we are discussed what are the definition of eigenvalues and eigenvectors. And some problems are discussed, how to find the eigenvalues and eigenvectors are based on the square matrices. So now we discuss about how to use the properties for finding the eigenvalues and eigenvectors in this session. So here we discuss some properties of eigenvalues and eigenvectors. The first property one is so lambda is a characteristic root of a square matrix A if and only if there exists a non-zero vector x such that Ax equal to lambda x. So here you have to prove that this property. So here we take the lambda be a characteristic root of, that means the eigenvalue of A. But then you can write its characteristic equation. Determine A minus lambda is equal to 0. So the determinant A minus lambda is equal to 0. So then A minus lambda is a singular matrix. But then you can write the homogeneous system of equations given by A minus lambda I into x is equal to 0. So here we get the possessive non-zero solutions of this homogeneous system. There exists a non-zero vector such that. So then you can write A minus lambda I into x equal to 0. Then it can be written as Ax minus lambda I into x equal to 0. Finally, you can prove Ax equal to lambda x. So conversely, it has to prove that write the Ax equal to lambda x. Then we can write it Ax equal to lambda x is in the form A minus lambda I into x equal to 0. So where x is a non-zero vector. So then the system is also a homogeneous equation. And here the system has a non-zero solutions. But then you can write A minus lambda I, the matrix is singular and its determinant value is equal to 0. That means determinant A minus lambda is equal to 0. So which shows that lambda is an eigenvalue of A. This is the property 1 of eigenvalues and eigenvectors. Now we are going to the second property of eigenvalues and eigenvectors. So here we take the square matrix A. Then we take the square matrix A. Then you can multiply and you take the capital X be an eigenvector of the square matrix A corresponding to the eigenvalue lambda. Then here we can multiply a non-zero scalar k with x is also an eigenvector of A corresponding to lambda. So k be a non-zero scalar. So here we can prove that this property lambda is an eigenvector of A corresponding to the lambda. Then you can write Ax equal to lambda x. Then you can multiply this equation both sides with a non-zero scalar k. Then it can be written as A into kx is equal to lambda into kx. So which proves the result. So lambda is an eigenvalue of A. But then kx is also eigenvector of A corresponding to the eigenvalue. This is the one of the property. Next, we got the third property of eigenvalues and eigenvectors. Then here we take the square matrix A. The lambda is an eigenvalue of A. Then the k lambda can multiply the eigenvector with a non-zero scalar k. Then k lambda is an eigenvalue of ka. Then k is a where k is a non-zero scalar. Then here you can prove that. So write x be a non-zero vector. X be a eigenvector of A corresponding to the eigenvalue lambda, then you can write the equation is Ax is equal to lambda x. After multiplying this equation both sides by with a non-zero scalar k, then you can write k into x, k into ax. Finally, you can put k into lambda x and k in lambda into x. Then it is called then ka. That means k lambda is eigenvalue of the matrix Ka, which proves the result. Now we go for the another property of this one. Here we can prove. Suppose here B is a non-singular matrix of and A comma B are matrices of same order. Then A and B inverse AB have the same eigenvalues. That means B is a non-singular matrix and A comma B are matrices of same order. Then we have to prove that A and B inverse AB have same eigenvalues. So here we take A and B are of same order. Then we can write here with our assumption, we take the another matrix C. C is equal to B inverse AB. Now we have to prove that A and C have the same eigenvalues for that. So C is equal to B inverse AB. Then you can write the C is equal to C minus lambda I. So in the place of C, you can replace by C by B inverse AB. Then you can write B inverse AB minus lambda into B inverse into B. So that means until here we take the place of I by B inverse B. Then finally we get the result is B inverse AB minus B inverse lambda B. Then you can common in the left side on the right hand side. B inverse is common in the right hand side and B inverse A minus lambda I into B. Then you can apply the determinant on both sides. We get determinant C minus lambda I is equal to determinant B inverse into determinant A minus lambda I into determinant B. Determinant C minus lambda is equal to the determinant B inverse into B is equal to 1. Then determinant of C minus lambda is equal to determinant of A minus lambda I. So here the determinant values, that means the characteristic equation of C, the characteristic equation of A, both are same. So the two matrices have the same eigenvalues. So now we can go for the another property here we discuss. So if the lambda, here we can take another property of eigenvalues and eigenvectors. Lambda is an eigenvalue of a non-zero scalar of a non-zero singular matrix. Then we have to show that determinant A by lambda is an eigenvalue of the adjoint of matrix A. Already you know what is the adjoint matrix of a square matrix. So then we can write that means the adjoint matrix of means that is the inverse of the cofactor matrix. Already you know that what is the adjoint matrix. Here also same. That means lambda is an eigen value of a matrix square matrix A is a non-singular matrix C. Then here we take the x be a eigenvector of corresponding to the eigenvalue lambda to the matrix A. Then you can write Ax is equal to lambda x. Then you can multiply on both sides of this equation by adjoint A. So adjoint A into Ax into adjoint A into lambda x. Then you can write, already we know that the inverse of the matrix, that is means A inverse is equal to already A adjoint A by determinant A. Then you can apply this formula in the place of adjoint A. Then you can write in the place of adjoint A by determinant A into A inverse. Then the equation, the resulting equation is determinant A into x is equal to adjoint A into lambda x. That means we can reshuffle the equation, determinant A by lambda into x into adjoint A is equal to x. Then this equation is comparing with the ax equal to lambda x. That means adjoint determinant A by lambda is an eigenvalue of adjoint A. So which proves the statement of the this property. And there are so many properties are discussing the next time. See here, that is another one of the properties. The here we have to prove that the eigenvalues of A and its transpose. That means A transpose have the same eigenvalues. Then you can write the matrix of A, the characteristic equation of matrix A and the characteristic equation of A transpose, that can be having the same characteristic equation. That is the two characteristic equations are same. Then the matrix A and its transpose A transpose having the same eigenvalues. For this, we have to prove that. So first we can write the characteristic equation of A. That means determinant A minus lambda is equal to 0. Then you can apply the transpose of this matrix A determinant. So then you can determine A minus lambda I whole transpose. Already we know that AB whole transpose equal to A minus B whole transpose equal to A transpose minus B transpose. So that why you can write determinant A transpose minus lambda I whole transpose. That is equal. Finally, we get determinant A transpose minus lambda I. So this shows that the two matrices A and A transpose are having the same eigen values. The next, the another property is if A is non-singular matrix and lambda is an eigenvalue of A, then we have to show that 1 by lambda is an eigenvalue of A inverse. And that means A is a non-singular matrix and lambda is an eigenvalue of A. Then 1 by lambda, that means lambda inverse is an eigenvalue of A inverse. So that it can be so that same. Here we also take our assumption the xb an eigenvector of A corresponding to the some eigenvalue lambda. So then it can be written as Ax equal to lambda x. Then you can apply, then you can multiply both sides of the LHS and RS, multiply with the A inverse. Then you can write A inverse into Ax and to A inverse into lambda x. In the left hand side is the matrix multiplication is associative. Then you can write A inverse into A into x is equal to A inverse lambda into A inverse x. That means Ix is equal to A into A inverse is equal to I. So Ix is equal to x. Okay. So some more properties are discussed in the next class. I 5 minutes. Lalu, Nura.